this sneaking onto the internet. Sorry. I know it's unlikely, but okay, we're live. So what was the magic function we developed at the end of class? By integrating one of our first power series, term by term. We integrated, yes, we revised that to be 1 over x, and we integrated it, and we got a series for the natural log of x. We found the natural log of x was equal to x minus 1 minus x minus 1 in parentheses squared over 2 plus x minus 1 in parentheses cubed over 3, right? We got a pattern going on here. X minus 1 to the 4th over 4, dot, dot, dot. It keeps going like that forever and ever. So we found a power series, and we could summarize it in the following way. Series goes from 1 to infinity of x minus 1 to the n over n. Nice, cute, little, simple series. It's kind of neat. It's what we ended up with by manipulating a sequence, the geometric power series that we started with. Right? That's the geometric one, is the most basic power series. Now, to get here, we had an interval of convergence. And the only thing questioned about the interval were the endpoints. Does anybody remember what the interval was? Or at least, what was it centered at?
Oh, 1.
It was centered at 1, right? And this is super important with series. Generally, that number right there is your center. No, the number that's along with the x. So since this is x minus 1, that means 1 is the center. All right, so we got 1 is the center. Anybody remember the radius that we started off with for this particular one? It was 1 also, yeah. So we had a radius. So we inherited here a radius of 1. Inherited a radius of convergence of 1. So if I know the center and I know the radius, I can always write that as an absolute value inequality. So the absolute value inequality is always going to look like this. It's always going to be x minus whatever the center is. What's my center? 1. Right? So I'm going to call that C for center. And then it's going to be less than that absolute value, the radius. What's my radius? 1. It happens to be 1 too, so that's my radius, right? So in general, absolute value of inequalities, x minus some center in absolute value is less than some radius. That'll give you an interval, radius r, centered at C. Right? So if I draw that on a number line, 1 is the center. If I go out 1 unit to the right, that puts me at 2. 1 unit to the left puts me at 0. And so open circles on each end, that's my interval right now. So what we believe is that if x is some number between 0 and 2, and we plug it in for x in this series, the series will converge, and the value it converges to will be whatever the natural log of that number is. Well, any number in this interval, right? So is 1/2 in that interval? Yeah. Okay. So then, according to this, the natural log of 1/2 is equal to parentheses 1/2 minus 1 minus 1/2 minus 1 squared over 2 plus 1/2 minus 1 cubed over 3, and so on, minus 1/2 minus 1 to the 4th over 4. Keep going. I can clean that up a little bit. 1/2 minus 1 is what? The first one, negative 1/2. So the first term is negative 1/2. Okay. Then I'm going to have a minus the second term. For the second term, it's going to be negative 1/2 squared, which is 1/2 squared over 2. What's the third term going to be? Negative 1/2 cubed. So it's going to be negative 1/2 cubed is negative. So I'm going to have, and I can rewrite it as 1/2 cubed over 3. Notice that all these things are negative, so my answer is going to be negative. It's interesting. What's next? It will be minus 1/2 to the 4th, oops, over 4. Okay. And I can rewrite that a little bit, so I'm going to rewrite it just for fun. I'm going to pull out the negative, and then everything left behind is going to be positive. And so then I will have 1/2, and I'm going to rewrite it like this: 1 over 2 squared times 2 plus 1 over 2 cubed times 3 plus 1 over 2 to the 4th times 4. Okay, so if, oops, red. If x is 1/2, I will get this, oops, wrong color. I will get this particular series, which I think I can rewrite that as in summation notation, right? Put a negative in front, summation, n's going from 1 to infinity, 1 over 2 to the n times n, which is a twisted geometric series, right? So now I already know this converges. How do I know this converges? Yeah, because the power series converges. I started off with the idea of a convergent power series. Plugging in a number for x led me to an ordinary series, right? No x's. These are the stuff we were doing in the first, the sections 10.2 through 10.6. Right? And if I didn't know it already converged, what test might I have used on this black series here? I would probably use the ratio test, yeah. Or the nth root test would work too here. Okay. But I don't even need to do that. I already know it converges. Now here's the problem back in those other sections. In those other sections, we would have looked at this and said, let's use the ratio test. We would have done a whole bunch of work, and the ratio test would conclude that it's convergent. And then we were done with it. We didn't know what it converged to, all we knew it converges. The power series tells me not only does it converge, but it converges to that number. Let's test that numerically. Isn't it exciting? I'm excited about it. All right, so I'm going to use GeoGebra to test this sucker out. So in GeoGebra, I'm going to go negative, and I'm going to add up a bunch of terms. So let's see. I want to do then a sum sequence. Oops. And my expression is 1 divided by parentheses 2 raised to the n times n. Close the denominator. My variable is n. I'm starting at what? 1 or 0, 1. We want to get that right. And let's say we want to go out 100 terms. Okay. And then enter. Okay, GeoGebra says it's about 0.69-ish. Let's blow that up so we can see this on the internet and get more decimal places. Let's go out 10 decimal places, big screen. All right, now we believe the answer is the opposite, is the, let's see, natural log of 1/2. And whoa, look at how many decimal places of accuracy I got there. That's converging pretty damn fast. 100 terms, and I already have a lot of decimal places of accuracy. Geometric series tend to converge fast. Is this a geometric series? It is, right? Well, a twisted version of one. It's close to one. Right, in the ratio test, or a limit comparison test. Would that have worked here? Could I have used a limit comparison test on this black series? What sequence would I compare it to with a limit comparison test? No, not 1 over n. 1 over 2 to the n. You'd compare it to 1 over 2 to the n. Yeah, so if you were going to use a limit comparison test on here, this would be the comparison series right there. Yeah, 1 over n is divergent, so that wouldn't help in comparison. And this isn't similar enough to n squared, so that wouldn't help either. That wouldn't lead anything useful, I don't think. I don't know. I don't think it would. We could try that later. 1 over 2 to the n. Oh, okay. Yeah, we would compare it to 1 over 2 to the n in a limit. We'd take the ratio of the two of them and take the limit, and that would show it's convergent. All right, so the power series, they have a lot of useful things. One thing is now, every once in a while, we will develop a power series, and we'll say, hey, wait, that looks like a regular series we analyzed earlier, and earlier we could just say it converged, but we didn't know to what. Now we know to what it converges to. Now, will we be able to find a power series to represent any of the regular series we saw before? Probably not. Maybe they're related, but sometimes it's hard to find one that matches stuff you've seen before. Because we only have a few tools to work with. What are our tools so far for generating power series? Let's see. So generating power series. Okay. So the first section, remember, that was just on sequences. Sequences are just limits. The next 5 sections, those are on infinite series, which are just lists of numbers to add up. Power series are infinitely long polynomials, which is a whole nother step up in complexity. And by generating here, I kind of mean discovering. So what we're working on right now is we're discovering new infinitely long polynomials. Now, polynomials is generally something of fixed length. These are infinitely long, so they get a special name, and they're called power series. The most basic one we've generated so far was the sum as, oops, wrong variable, n goes from 0 to infinity of x to the n, which is just 1 plus x plus, that's a plus, x squared plus x cubed, dot, dot, dot. And we know because that's a geometric series that that converges to 1 over 1 minus x if the absolute value of x is some number less than 1. That was our starting, our first power series. We messed with that by doing some substitutions, replacing x with negative x, replacing x with 1 minus x. And other things we can do is we can integrate and differentiate it. Okay. So we integrated a substituted version of this and got the series for natural log of x. Now, our series was centered at 1, right? So for natural log of x, what's this series centered at? 0, that's correct. If you look at that interval right there, you could rewrite that as x minus 0 is less than 1. And so 0 is the center. Okay. What's my radius for this one? 1. Radius. Come on. There we go. Center. All right, so in general, power series look like this. Let's see, A sub n. That's kind of a general power series. Coefficients are the A sub n's. They can be all different kinds of things. In my previous one, they were always 1. My center was 0. With the natural logarithm, the A sub n's, let's look back. Well, the first one would be a 1. This one right here would be a negative 1/2, positive 1/3, negative 1/4. Those would be the coefficients of the powers of x. So that'd be something like negative 1 to the, let's see, that one started at 1, so it would be an n plus 1 divided by n, or what the coefficients of that series look like. This series also had a center of 1. And using the ratio test, or some prior knowledge, we can find the radius of convergence. And so we're just going to play around today with finding centers and radius of convergence for different series, and then we'll go over a new way to discover series that I haven't talked about yet. So let's see, we're going to go back to the natural log series. Natural log of x we discovered was equal to the series x minus 1 minus x minus 1 squared over 2 plus x minus 1 squared over 3 minus dot dot dot, which I could write as the sum, n goes from 1 to infinity, of x minus 1 to the n, ooh, I forgot my little negative 1 to the n plus 1 over n would be this particular series. Thing you want to be careful about when you're writing down the summation form is if it's alternating, getting the power n or n plus 1 correct so that you have the signs in the right spot. And that depends on your starting point. Are you starting at 1 or starting at 0? Okay. So let's see, what do we know again? We know that this has an interval of convergence of x minus 1 and absolute value is less than 1, which puts us on the interval between 0 and 2. If series are generated from other series, then they're going to inherit an interval of convergence. But the endpoints might change behavior. So you always got to recheck endpoints. So we have to see what's happening if x equals 0. And we need to see what's happening if x equals 2 to this series. So what happens if I replace x with 0? That's going to give me the sum as n goes from 1 to infinity. I've got my negative 1 to the n plus 1. And then I'm going to have 0 minus 1 is negative 1 to the n over n. So we have to clean that up a little bit. What should we do next? Yeah, before we do that, though, we want to clean up the numerator a wee bit because we have multiple n minus 1s. So I'm going to tweak that a bit. So let's go to a new page. So the sum n goes from 1 to infinity. So the negative 1 to the n plus 1, I'm going to rewrite that as negative 1 to the n times negative 1 to the 1. And then I have my other negative 1 to the n. Right? So here's, right, this is my negative 1 to the n plus 1 right there. Well, what's negative 1 to the first? Just negative, and that's a constant. I can pull the constant out. So I'm going to pull that constant out. And then my sum here, n goes from 1 to infinity. What happens if I multiply two bases with the same power? They multiply. Right, sorry, yes, they add, you're correct. Yeah, same base, so that means I'm going to have negative 1 to what power? 2n, okay, 2n, all right. Now what that means is, I could look at it this way, I could view that as a power to a power, which would be negative 1 squared, then to the n. What's negative 1 squared? 1. Is this series alternating anymore? No. If we listed out the first few terms, we would have figured that out also. So what we have now is negative 1 times the sum as n goes from 1 to infinity of 1 over n. Now what do we know? What can you tell me about the sum of the 1 over n's? It's the harmonic series. It's divergent, yeah. Okay, so is there a chance we messed up playing with the numerator? There's always a chance, so maybe I should list a few terms to kind of see what's going on. I want to. Yeah, no, I think we should, right? If this was on a test, you should do it, right? You want to know for sure. So the original said n goes from 1 to infinity of negative 1 to the n plus 1 times negative 1 to the n over n. So if n equals 1, I'll have in the numerator 1 times negative 1 over 1. If n equals 2, then this negative 1 would be 2 plus 1, it'd be cubed. Negative 1 cubed is negative 1. Negative 1 squared is positive 1 over 2. If I plug in n equals 3, then I'll have negative 1 to the 4th, which is positive 1, times negative 1 cubed, which is negative 1. Okay, so we're starting to get a feel for what this is doing? It's all, yeah, so this looks like I have a negative in front always. 1 minus 1/2 minus 1/3 minus 1/4 is going to be next. Dot, dot, dot. So this is, oops, I meant to put an equal sign and a pen. So this equals the opposite of the harmonic series. 1 plus 1/2 plus 1/3, dot, dot, dot. Which is what we saw algebraically when we were messing around up top. Okay. So I always like to list some terms and play around with them and do whatever I can with tests and cleaning things up. Okay. All right, so we found, if we go back a step, that we diverge at the left endpoint.
All right, that was just the 0.
We still have to do the 2 now, yeah. Power series are a lot of work. Okay, so for the 2, we're going to have the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times, let's see, 2 minus 1 is 1, so that's going to be 1 to the n. All right, 1 to the n, that's useless. So what do we really have here? Looks like the alternating harmonic series. 1 minus 1/2 plus 1/3 minus 1/4. What do we know about the alternating harmonic series? No. Why does it converge, Jeff? The alternating series test should tell us it converges. So let's check it out just to make sure. Okay. Yeah, that was a problem on the test, distinguishing between sequences and series and what stuff you use for sequences. I'll tell you later. The test looked pretty good, but there were some problems with that. Sequences are just limits. 1 over n as a limit, as n goes to infinity, goes to 0, which means it converges. Yeah. With limits, if you get a number, it converged. How do limits diverge? Or infinity, negative infinity, or what? Anna? Jeff?
How many of those converge?
All of them.
All of them.
Shh. Hopefully William already took it before he sees this recording. What things causes a sequence, which is a limit, to diverge?
Goes to infinity.
If it oscillates, yeah. If it oscillates, it doesn't settle down on a number, or if it goes to infinity or negative infinity, that's what diverges as a limit. Okay, we'll talk that when I'm not broadcasting. Yeah. All right. So the alternating series test, 3 conditions. First condition. First condition.
Sorry.
Worry about that later.
Everybody's mad now.
Strictly alternating. Okay. If it's strictly alternating, okay, focus. Come on, come on.
Sorry.
Forget about it. Focus.
Hold our test.
Let's see. If it's strictly alternating, then the remaining thing should be greater than 0, right? If I remove the strictly alternating part, the remaining part is greater than 0. That's true here, right? Second rule of the alternating series test, that if you ignore the alternating part, you check to see if it is monotonic decreasing. Is it true? Yeah, we can pretty much look at that and see it. 3, is it true that the limit as n increases of 1 over n goes to 0? Yeah, okay. So that implies this thing is convergent. Yes, so let's back up. Now we did that one in class before. We found it converges at this endpoint. So we can shade that circle. Now, that was like the first alternating series we did, the one we just analyzed. It was the first one we did. But all we could say was it converged. Now what can we say? No. If x is 2, that gives me this series. True? Well, isn't this series related to the natural log of x? For which x value? So that means this series must be equal to the natural log of 2. Not only can we say it converges, but the power series tells what it converges to, because we were able to link this function to this series. Let's test that. Is that true, or am I making this shit up? I might be making this shit up. That's possible. All right. So let's see. I'm going to delete. Oh, actually, I can just modify this series. Okay. So I want to just have a numerator. Let's see. What do I want here? I want, instead of 2 to the n, I want -1 to the n, right? Because it's alternating. And then I want to divide by n. I think I have the right series there, right? -1 to the n. Oh, -1 to the n plus 1. Good thing you wrote that down there, Jeff. And where are we starting this at? 1 or 0? We're starting at 1. Okay, we always got to double check that. And let's do 100 terms, and we'll apply that. Come on, I hit apply. Oh, something happened. Okay, so it says the answer is -0.688172. Now let's actually calculate that number. Let's delete this guy. I guess we don't need you anymore. Delete. What number do we think that is? Natural log of 2. Oh, shit. Oh, I didn't add enough terms. Oh. Oh. What did I do? -1 to the n. Oh, I put a negative in front of it right here. That was the previous service one we did. Sorry, I was trying to rewrite the one we did earlier. Apply. Oh, there we go. Okay, now, hey, it doesn't look that close. What's the matter? I only have 1, maybe 2 decimal places of accuracy.
Yeah, what's the deal with that?
Yeah, what's the deal with that? Oh, wait. Don't we have a remainder theorem?
Oh.
Oh, how many terms do we need to get enough decimal places of accuracy? Oh, let's. Is 100 terms enough to add up and get 2 decimal places of accuracy here? Well, maybe it's close, but let's check. All right. What does the remainder theorem say for alternating series? Oh, that was quiet. The remainder theorem says that the error, the remainder in absolute value, has to be less than or equal to the next term, which we call u sub n plus 1.
Wait, I knew the answer to that.
Okay. All right. So u sub n plus 1 for us is 1 over n plus 1.
Wait, what? Oh, wait, yes.
right? Because our series is 1 over n.
Yeah.
Ignore the alternating sign.
Yeah.
That's what the u's do. All right. So let's suppose I want 2 decimal places of accuracy, meaning that when I subtract, I get 2 zeros, and then who cares what comes next? Maybe a 1. So I want my 1 over n plus 1, say, to be less than that. Because 1 over n plus 1 is an approximation of my error. Okay. Well, this is really 1 over 1,000. So I want 1 over n plus 1 to be less than that, which means n plus 1 has to be greater than 1,000, or n has to be greater than 999. How many terms did I add? 100. I didn't add enough. All right. Let's add a few more terms. Is all this starting to fit together a little bit?
Yeah, sort of, kind of.
Sort of, kind of, okay.
When I practice it.
It needs more practice, yeah. Hey, look at that. I got 1, 2, almost 3 decimal places of accuracy. Now, why am I saying the third one's questionable? Because typically we would round that and we'd call it 694, okay, instead of truncating. So we're close. If I subtract these two, are they about 0.001 apart? Let's double check. Let's take B minus A in GeoGebra, and GeoGebra says that's 0.0005. If we round that, that's close to 0.001, which is what I was aiming for my error. Okay. Now here we actually know the exact sum. B is the exact sum, the natural log of 2, 0.69314711806. All right. So I'm going to give you a couple more series, and we're just going to mess around and see what happens. So what we're going to aim to do is when I write down a series, we want to identify the center of convergence, and we want to identify the radius of convergence. Okay. Do all power series converge? No, they don't. Right? But most of the ones we look at will. Should I have said that? I am a little biased on convergence, yeah. Sum, as n goes from 0 to infinity, of x to the n over my favorite thing, n factorial. I love n factorial. All right, so if I list some terms here, if n equals 0, does anybody remember what 0 factorial is? It is 1, right. So I'll get x to the 0, which is also 1, so the first term is 1 here. Then I will get a plus x over 1 factorial, which is just x. Then I will get x squared over 2 factorial, which is 2, x cubed over 3 factorial, which is 6, and this is going to keep going. What's the nth term going to be? Well, it's going to be x to the n over n factorial. And whatever that n is, it keeps going. So this is the infinite polynomial that I'm messing with here. I want to identify what is the center of this particular power series. And that you can tell just by looking at it. Oops, there we go. What is the center of the power series? 0, that's correct, yeah. You can tell the center by looking and see if it has x minus some number c. In this case, c is equal to 0, so that's the center. Okay, so if it's just powers of x, what's the center? 0, yeah. If it were instead powers of x minus 5, no. Yeah, the center here would be 5.
So then if it was x plus 5, it would be negative.
If we put a plus 5 there, then the center would be negative 5, correct? Yeah, you got the center thing now? All right, center's the easy part. You look, oh, there's the center. Okay, hard part, radius. Oops. Okay, radius. Radius, we either use the root test or the ratio test. What's our best friend for factorials?
Definitely the ratio.
The ratio test, right. So the ratio test, I want to take the limit as n increases. From now on, you're going to put absolute value when you do the ratio test. Very important, because you have to. Why? Because we have x's. We don't know if x is positive or negative. All right? So I have x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And then we attempt to clean this sucker up. All right, so let me see. Limits is hanging out. What happens with the x's? Yeah, x to the n plus 1 over x to the n is just x. What happens with the factorials? On the bottom, yeah, right, because n factorial is n times n minus 1 times n minus 2, blah, 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 all the way down to 2 times 1. N plus 1 factorial is n plus 1 times n minus 1, all the way down to 2 times 1. And so a whole bunch of stuff cancels, and I just love writing this down so I can go whack, whack. All right, so there we go. N plus 1 is in the bottom. All right, as n gets big, x is fixed. Could be 2, could be 1, could be 100, doesn't matter. It's fixed. What's happening here as n gets big?
0.
Yeah, the denominator is getting huge, the numerator is fixed, this thing goes to 0. What does the ratio test say about this limit? If what's true? If the limit is less than 1. Yeah, if it's less, no, well, yeah, a constant less than 1, right? Which, yeah, good. Yeah, is this less than 1? So the ratio test says this converges. Now, wait a minute. No, we didn't know this thing converged. Did not. We didn't. I knew, but you didn't. Not for sure until we finished the test. Now, wait a minute. What happened to x? Does it matter what x is?
No.
If x is 10 or 100 or e, it still converges, right? So that means this converges for all x, because the x disappeared. In our problems the other day, it didn't disappear. For all x.
Pretty mind
Okay, so what's the radius?
0.
No, 0 would mean it doesn't converge outside of the center. Nope. If the radius was 1, that means it would only converge between -1 and +1. The radius is infinite. Yes, the radius is infinite. Yeah. This tells us that R is infinite. That's a weird R. Yeah, you can have an infinite radius. This converges for all real numbers. That's an infinite radius, centered at 0. No matter what x is, this converges.
Oh, yeah. Oh, I see it now. Yeah, I see it now.
So here's the deal, right?
This means it always.
This series, oops, eraser. This series right here, no matter what x value I plug in, will converge.
I like that. Never mind. Go infinity.
Okay, like suppose 7. Let's say x is 7. We love 7. 7's a wonderful number. If x is 7, why am I sitting down?
My favorite number is 21, which is 7 times 3.
That is, oh my gosh, that was quite a coincidence. All right, so check it out. We're going to do the sum, oops. We're going to do the sum as n goes from 0 to infinity. I'm going to use 7 because I like 7. That means I'll have 7 to the n over n factorial. Okay. Do we know that this isn't a power series anymore? It's an ordinary series. Does this ordinary series converge? Yes, because the power series said so. We just did all that work on the other page. We just determined that anything that looks like this will converge. That's what the work on the next page is all about.
I agree.
Converges for all x. That's what we just found out. Now, if we didn't already know that, we would have to use like the ratio test on that. But we just did the ratio test.
So why do it again?
Right. We don't have to do it again. I know this converges.
Hey, this is actually kind of a cool thing. It is. I like it.
Right? Because the previous work, right? See last page.
Yeah, that would be fun. I want to see that.
N to the n, that's, yeah, good. Okay, we'll do that in a minute. It has, yeah. N to the N is what we've worried. Okay, focus. Okay, let's estimate what it converges to. Okay, now, if I wanted to be able to use a remainder theorem on this, I have two choices for remainder theorems: alternating series or integrals. Okay, is this alternating? Okay, can we take the integral of a factorial?
I don't know how.
We can't. We can't here. Okay, so can I apply one of my remainder theorems? No, I can't. All I can do is just list out some terms and see if I can kind of see decimal places starting to get fixed. So we're just going to do a few partial sums. Go for it. N equals 0 to something. 7 to the n over n factorial. Do a few partial sums. Pick some numbers. See what happens. Need a calculator? What? Numerically evaluating. We are numerically evaluating this series by picking some ending values, some partial sums. Like, I'm kind of curious, can my calculator do S sub 100? I don't know. Let's ask the TI and we'll ask GeoGebra. Let's see. Quit. I want to. Oh, I have that secret button. There we go. So I want to sum. X goes from 0. Where are we starting? 0, not 1, right? I'm going to go up to 100, see if my calculator can deal with it. 7. Yours is struggling.
Well, I'm only at
X math factorial. All right, so we'll let that sit a minute. I'm going to go ask GeoGebra and file. Don't save.
That's what I got too. Yeah.
All right, so by the way, I just want to show you this sum sequence.
Actually, 30.
X raised to the n divided by n factorial as n goes from 0 to, let's go 20. All right, here's a graph of the 20th partial sum. Oops. Okay, so if I do that for a second, there's a graph of the 20th partial sum. Now notice it does something weird there on the other side. But if I just look at that part, does that remind you of any function you've seen before?
Yeah, it does.
Like what? It looks like an exponential function, like maybe e to the x, huh? Maybe let's graph e to the x. E raised to the x. Holy shit. Sorry, did I ruin your surprise? This looks like e to the x. Don't they sit right on top of each other?
That's so cool.
All right, let's make this back one pink and dotted and fat. Color pinkish. Style dotted. Size nice and chunky. Look at that, it sits right under e to the x. Now, does it always sit right under e to the x? I didn't add enough terms, so it diverges to the left of -7. And because of its steepness, it's hard to see where it diverges on this side, but it does diverge somewhere. But this is a rapidly growing function, ain't it? So when we plugged in 7, we are estimating the value of e to the 7th. E raised to the 7th, because we picked x to be 7, didn't we? E to the 7th is 1096-ish.
Yeah, that's what we got.
Oh my gosh, let's go see if my calculator's still chunking along. Ooh, overflow, can't do it. I tried to go 100 terms.
I got 28.
You went to 28 terms and you got a pretty good estimate? Okay, so let's try GeoGebra. So I'm just going to do a sum sequence on GeoGebra because it can go a little farther. And my sequence is 7 raised to the n divided by n factorial. N is my variable starting at 0. And you went to 28. I'll go to 28. What the heck? And GeoGebra says it's 1096.6331. Ooh, that's pretty good. We got like 5, 6 decimal places of accuracy there. Nice. Isn't it exciting?
That was a really good idea.
Okay, now we just accidentally discovered that that looks like it's e to the x.
I don't know if we accidentally
I do think it's
You
cool
had
that we
to-
did.
I think you had to draw that.
No, I didn't. I said, what does this graph look like? You said exponential. C said e to the x or ln of x. ln of x would be a flip of this through the line y equals x, right? Because they're inverse functions, right? Yeah. And isn't this amazing?
Yeah. I also think it's cool.
I think it's amazing. Okay, so wow, let's do a couple more playing arounds here, and then we'll see if we can prove that it really is e to the x. Because right now we just got this hokey pokey visual idea, right? Oh, come on, we'll prove something. Let's see. How about? Oh, that's a cute one right there. All right, so here's a new power series. Oh, do we need to check endpoints here? No, the radius is infinite. There are no endpoints. Isn't that nice?
I like it.
Yeah, the endpoints. Yeah, if the radius is positive, you still have a lot more work to do, right? Which is okay. New. My page is out of order. Nope. All right, I'm doing good today. How about the sum as n goes from, what did I put there? A 1. Yep, a 1 to infinity, negative 2 to the n times x minus 3 to the n over the square root of n plus 3. That's our power series. We're going all out here. Okay. So sometimes it's not the center is 3. Excellent. Write that down right away. Center is 3. So now we just got to hope for a radius. What are we going to do to try to find a radius? Oh, then we'll have the nth root of a root ratio. I like the ratio. We could use the nth root here.
No, I like your idea better. Just stick with your guess.
Now we're going to do the nth root. What the hell? I haven't done it in a while. Okay, so the nth root test, take the limit as n increases of the nth root. I have used it at least once, maybe twice.
Use it and be like, oh, that didn't work, so let's do the radius.
How do you take
Absolute value. You got to have absolute value.
the nth root of the square root?
Yeah, we just do. I'll show you. I got an idea. All right.
Learn.
So let's see. Then we just plug this stuff in. Negative 2 to the n times x minus 3 to the n all over the square root of n plus 3. All right. Oops, I'm missing that, and then let's end that. And I always put a little hook at the end of my square roots to be clear where they end, and then I try to make this part go down far enough to be clear what's inside and what's not. All right, so negative 2 to the n is going to oscillate, right? Positive, negative, positive, negative. I only want the absolute value of that, right? So I'm just going to call it 2 to the n. Okay. Now, as far as the x minus 3 goes, that's going to bounce around a lot, and I really have to leave the absolute value around it. Okay. Because it's going to constantly change. So I'm kind of stuck with that. And then nth root is really the power of 1 over n, right? We could think about it that way. Now, the nth root of n, what happens there? It cancels, right? So there's a 2. So far, let's clean up the limit. N is going to infinity. Let's change color. So we're going to have a 2 in the top. We're going to have the absolute value of x minus 3 chilling out there. And then in the denominator, we could either write it as the nth root of the square root, or we could say that we have an n plus 3 to the power 1/2, and that is to the power 1 over n. Okay. All right. This isn't looking so bad. I think we can handle this guy. There we go. All right. So this is the limit. Actually, hang on. I'm going to write this a little bit different. Does 2 have anything to do with n?
No.
Does the x minus 3 have anything to do with n? They all come out. I just pull this out of the limit. So outside the limit, I'm going to have 2 times the absolute value of x minus 3. Then I'm going to have the limit as n increases of 1 over power to a power. We do what with them? Multiply them. So that's going to be an n plus 3 to the power 1 over 2n. Ooh, interesting. What is that doing?
Always graph it.
We could. We could list a few terms. We got lots of options. So I'm just going to separate out the troublesome part here. So the troublesome part is the limit, and check this out too. There's no n's in the top, right? So this is the denominator of this thing. I got to figure out what it's doing. I just got to figure out what the denominator is doing. All right. Limit as n goes to infinity. We need that, what was it, n plus 3 to the power 1 over 2n. We got to figure out what that's doing. Now, if I cheat, what happens? Well, if I cheat, the base is infinity. And what's the power doing? It's going to 1 over infinity, which is, so this looks like cheating. This looks like infinity to the power 0. Ooh, that's weird. Right? Infinity is getting big. Things to the power 0 become 1. So I have some indeterminacy going on here. Oh, L'Hopital's rule applies to things like 0 over 0 or infinity over infinity.
So we
We could rearrange it. Okay. What do we need to do to rearrange it? Well, the problem we have here is that we have n in the base and n in the power. How do we get things out of the power? Natural log. Okay.
Nicely done.
Good job. Okay, so we're going to assume this thing has a limit. We're going to call it L. And we are going to take the natural log. By the way, if we did the ratio test, I don't think we would have had to do all this work, but that's okay. The natural log of L is equal to, and I'm going to bring the natural log inside, so I'm going to say this is the limit as n increases of 1 over 2 to the n times the natural log of n plus 3. Right, because the natural log lets me bring the power down. All right. Rewriting this a little more, I'm going to say this is what happens here. Well, let's cheat again, maybe. If we try to cheat and plug in infinity, we get 0 times infinity. So maybe I should write it like this. Limit as n increases of the natural log of n plus 3 over 2n. Is that true? Okay. Now if I cheat, what do I get? I get infinity over infinity. Now we can use what? Now we can use L'Hopital's rule. So we apply L'Hopital's rule, and that gives us the limit as n increases. Derivative of the top is what? 1 over n plus 3. Derivative of the bottom? Nope.
No, it's just 2.
It's just 2, yeah. Okay, so now I have the limit as n increases of 1 over 2 times n plus 3. And that limit is, holy shit, we finally get a limit, sort of. Now what we have is that the natural log of L equals 0. So what must L be? E to the 0, which is 1. This goes to 1. Was there one like that on the test?
I'm pretty sure I got E to the 1. I'm pretty sure.
Yeah, you did have to use this on at least one problem on the test, maybe 2.
We're just learning about it now.
No, we didn't have a problem on the homework.
What do you mean? I've done this multiple times in class.
I have it in my notes.
Okay. Whew. What the hell were we doing in the first place here? Let's go back. Oh my gosh. Oh, we were trying to find the radius, and to find the radius, we had to take the limit of what the root test says, and we just determined that this denominator here is 1. Whew.
Pretty crazy.
Wow, it was a lot of work. Okay, so we have that this right, oops, that's not a pen. That's a pen. We found that this right here is equal to twice the absolute value of x minus 3. That's what we just discovered. We applied, which test is this again that I applied? The root test. Okay, so I think this problem might be one reason I tend to avoid the root test unless I really have to use it. So I think the ratio test would have been a little easier in retrospect. What does the root test say about my limit to have convergence? No. Has to be less than 1. Okay. So this right here has to be less than 1. Okay, let's analyze that next. Okay. So we had, let's back up a step, the sum from 1 to infinity of negative 2 to the n times x minus 3 to the n all over the square root of n plus 3. And we applied that the root test, and it gave us that twice the absolute value of x minus 3 has to be less than 1. All right. Now, this isn't quite in the form that I like. The form that I like is the absolute value of x minus c is less than some number r. So what should I do to tweak this black thing to look like the red thing? Divide by 2. Okay. So now I have the absolute value of x minus 3 is less than 1/2. So now I know my radius. What's my radius? It's the 1/2. The center of this is what? 3. So from 3, I can go 1/2 to the right, which is 3.5, and I can go 1/2 to the left, which is 2.5. And so now I know that this series converges between 2.5 and 3.5. So any x value in between 2.5 and 3.5, if we were to plug it in for x there, I have a convergent infinite series. And even better, I could estimate the remainder easily because this is an alternating series for most values of x. Oh, shit. Kinda. Well, here's the problem, right? If I pick a number on the right side of 3, right, they're like 3.1, and I plug it in up here, 3.1 minus 3 is what? 0.1. 0.1 to the n is always positive. If I pick a number on the left side, like 2.9, 2.9 to the n, 2.9 minus 3 is negative 0.1. To the n, that's alternating. And those alternating signs will cancel each other out. See what I'm saying? So my point is, if I pick a number on this side, the series will remain alternating. If I pick a number on this side, it will not alternate. Can you see what I'm getting at there? Yeah. So I can apply the alternating series remainder test to numbers between 3 and 3.5, but I can't on the other side. If I wanted to estimate remainders, what's my option? Integral test, and so then we'd have to try and take the integral of the coefficients. Right. Okay, so that might be pretty challenging. All right, so am I done? Am I done with the series? No, why not? We know it converges between 2.5 and 3.5. What are we missing? We don't know what's happening at the endpoints. Yeah. All we've determined is the center and the radius. We don't know what happens at the endpoints. We got to figure that out. All right, let's do it.
This is effort. Like, how many problems are on the homework for this section?
Not as many as on the other sections. And a test for this stuff would have to be much shorter. Like where I could ask you maybe 10 questions with regular series, I could only ask you like 2 or 3 for this one. Part take home. Part in class, yeah. Yeah. So x equals 2.5. Let's do that sucker first.
When do you think this test will be?
In a week and a half, 2 weeks, something like that. Sum as n goes from 1 to infinity of negative 2 to the n times 2.5 minus 3 to the n over the square root of n plus 3. Well, what's 2.5 minus 3? It's negative 1/2, isn't it? Okay, so that means here I'm going to have a negative 1/2 to the n. Okay, so that means I'll have the sum as n goes from 1 to infinity of negative 2 to the n times negative 1/2 to the n all over square root of n plus 3. What happens to the numerator here? Since the powers are the same, what do I get to do to the bases? I can multiply them together. You can do that with multiplication and division. Not with addition or subtraction. Don't ever do it with addition or subtraction. Yeah, so, okay, so these guys here multiplied together, what's negative 2 times negative 1/2? 1 to the n is still 1. So now my series looks like this. The sum as n goes from 1 to infinity of 1 over the square root of n plus 3. What kind of series does that remind you of? 1 over the square root of n, which is a p series. P is 1/2, which implies divergence. To confirm that, we are going to do what test? Limit comparison test. Oh, let's see, could it be a direct comparison? Let's see, if we add 3, so we're comparing this to the sum of the 1 over square root of n's, and if we add 3 to the bottom, that makes this one smaller than a divergent series. Is that helpful? No. No, this thing's growing forever. This one's underneath it. That's useless. So a direct comparison doesn't work. So what do I apply? A limit comparison, correct. Yeah. So we're going to do a limit comparison with that. Okay, so that means I have to take the limit as n goes to infinity. Does it matter which one's on the top or the bottom? Yes, which one has to go on the bottom? The known one has to go on the bottom. The 1 over the square root of n has to go on the bottom. Remember we ran into that trouble in class one day? We switched them and then everything went to hell. So 1 over the square root of n plus 3, 1 over the square root of n becomes the limit as n increases of those guys flip-flop, so that's the square root of n over the square root of n plus 3, which I could say is the limit as n increases of the square root of n over n plus 3. What can you tell me about that? It's going to 1, yeah. The limit can actually even go in the square root. Okay, you're with me? We're good? The limit's 1 there? All right. What does the limit of 1 mean for the limit comparison test?
Oh, it means that it's,
They both converge or they both diverge. Yeah, if it's a positive constant, that implies divergence. Because of that and that.
step once, and I was like, okay, because it's a constant, it does something. Then I was like, wait, that's not true.
Okay.
But then I changed it. So
That's the left end point. Guess what we have to do next?
the right hand.
The right end point. What's the right end point?
3.5.
Yeah, x equals 3.5. That means we have the sum as n goes from 1 to infinity of negative 2 to the n times 3.5 minus 3 to the n all over the square root of n plus 3. This is an alternating series this time. Okay, so cleaning this up, that's 1/2 to the n times negative 2 to the n gives me what? Negative 1 to the n. Beautiful. Okay, alternating series test.
It's always positive. U is decreasing monotonically.
I know what.
So n plus 1 is
1.
the limit. The limit goes to 0. Boom.
Alternates. Check. I know you told me. I was going to write it down. It's decreasing. 1 over n plus 3 plus 1 will be n plus 4 is definitely less than 1 over n plus 3 in the square root. Check. And 3. Limit goes to 0. Check.
Not all that fast.
Easy. Terribly easy.
It is wonderful. I love the alternating series test.
It's pretty great.
It's not always obvious, but most of them are. Okay, so this implies
Convergence.
convergence. Okay. Okay, convergence. All right, let's summarize what the hell we just did. Whew. This is like the biggest, baddest one we'll probably ever do. Oh, is that true? Oh, the next section has a couple badder ones. N equals 1 to infinity, negative 2 to the n, x minus 3 to the n over square root of n plus 3.
Next page.
All right. The center is what again?
3.
3. Okay. At the endpoint 3.5, it converges. At the endpoint 2.5, it diverges. Open circle. Okay. If I used interval notation, then I would say the interval is interval parenthesis 2.5, comma 3.5 bracket. Okay, now here's the big question. When is this thing absolutely convergent? Almost. Okay. It's absolutely convergent in the interval from 2.5 to 3.5. Why isn't it absolutely convergent at 3.5? No, we just said it's convergent. Yeah. So to be absolutely convergent, that means if we strip the signs, it also converges. But the previous page tells me if I strip the signs, it diverges. So that's kind of cool. One endpoint is the positive version, the other endpoint is the alternating version. That's pretty cute. Yeah. Okay, how do I know that in between it's absolutely convergent? How do I know that in between it's absolutely convergent? Because the ratio and root test require the absolute value of the ratio of the terms. That's why. Absolute convergence means we strip the signs and check to see if there's convergence. But at the endpoints, the ratio and root test are inconclusive. That's the reason. And the homework questions are going to ask you this. When is it absolutely convergent? When is it conditionally convergent? So we have absolute convergence anywhere in between 3.5 and 2.5, and we have conditional convergence when? At 3.5, yep. And conditional at 3.5. On the condition, we don't strip the signs, it converges. That's what the conditional part means. Absolute convergence means you can strip the signs and it will still converge. Right? Strip the signs is what absolute value does. Absolute convergence is all about absolute value of terms. Oh, can we take a 5-minute break?
Yeah.
All right.
That was a really intense problem.
That was an intense problem. I'm going to stop this broadcast and restart it, Zach. Zach left the group anyway. Okay, Zach. Hopefully you're going to watch this soon.